Thank you. Well, our speaker today is Daniel Neamati. He is wrapping up his ASP graduate visitor program visit. He's been with us for the past 2 months. It's been 2 months already?
3 months.
3 months, 3 months. It just flies by. He's been visiting Miles and working with us, plus meeting a whole lot of people around, not just NCAR, but NOAA, NEON. I know some of the folks on the call. Appreciate y'all chatting up Daniel and kind of getting into his world. Currently, for those who don't know him as well, he's pursuing his PhD at Stanford University in the NAV lab under Professor Grace Gow, and is a Tomcat Center Graduate Fellow for Translational Research. So he's like getting his degree in aerospace engineering, but it's like kind of this cross-disciplinary aerospace engineering thing, which is why he's here. And some of his, outside of his research, I mean, like photographing shrubs. And from what he told me, one of his favorite experiences in the Boulder area was hiking up the Royal Arch Trail, where there are quite a few shrubs to photograph. And his research is focusing on wildfire management using digital twins and distributed sensors with the Stanford SMesh team, led by Dr. Jessica Yu, who was here last week. So with that, I'll hand it over to Daniel to talk about burn or not to burn. That is indeed the question.
Awesome, thank you so much. And I've really enjoyed my time here with DJ, the whole team at NCAR, and especially the CISL Miles credit team. So, we're taking this meeting today from room 680 in the Mesa Lab here at NCAR. And if you look around, you'll actually see the smoke from some of the wildfires that we're seeing in Colorado and Utah. And I'm sure there's many people on this call that have either previously been impacted by fire, are currently being impacted by fire, or at some point in the future will be impacted by fire. So with that in mind, I do want to note that today we're going to be talking about prescribed burns rather than wildfires. And in terms of destruction, if you can think of it similarly to the destruction of a hurricane versus the benefits of a wildfire. And specifically, we're going to be looking at what might happen if we're willing to bring sensors with us into the field. So to start off with, I want to kind of immerse you into this scene. So this was a photo that we took at Pepperwood Preserve near Santa Rosa, California, during a prescribed burn in October 2025. And just, in this scene, think about like what you might see, hear, smell, and all that with a prescribed burn. But I want to kind of draw your attention to the fact that the intensity of the fire is a lot less than what you would see in a wildfire. So that being said, if you're new to prescribed fire, often the first question people ask is, why in the world are we even putting fire on the ground intentionally? There's many reasons for this. The first category of reasons is for wildfire mitigation. And specifically, if you have less vegetation in the area that the fire is going to be coming into, ideally you're aiming to inhibit the growth of the fire in one way or another. So you could be focused on just generally reducing the amount of vegetation, or if you have a very overgrown forest, you might be focused on disconnecting what's happening in the grassy understory with the overall canopy of the forest. And in this case, like the one at Pepperwood Preserve, you might be actively trying to manage a fuel break. So at Pepperwood Preserve, the place that they did this burn is a strategic spot to fight a wildfire if it were to show up in Sonoma County or into Napa County. The next reason is for some sense of training and improvement. So if you're able to do prescribed burns, you might be able to ensure that your evacuation routes, which is for the people getting out of the fire area, or the access route, which is for the firefighters getting to the wildfire area, are well maintained in a way that it's clear when the fire is coming through. You might also use a prescribed burn as a way to train firefighters, but so this could be early in the training, but even later in the training, the prescribed burn areas that people are operating in might be the places that those same people will hold a wildfire in the future. And the last part is you might be interested in demonstrating some amount of fire technology, whether that's for prescribed burns or wildfires, though keeping in mind that you're not going to get the severity of a wildfire in a prescribed burn. The third category is more cultural. There's a long-standing practice of prescribed burn more generally across the world, and it's a very important cultural practice that in some sense has to be reawakened from heritage, but in a larger sense is part of people's ongoing relationship with the land. And the last category is very ecological. So if you look kind of into the foothills of the Rockies and kind of more broadly in a lot of the forests that we have here in the Western United States, there is an aspect of tree health, whether it's from beetles or disease, that has produced a problem both ecologically and also for the wildfire situation. And prescribed burn can offer ways to ameliorate the situation, very broadly defined. And this is only a subset of the list. You know, we could keep going, but the point here is that there's many reasons you might do a prescribed burn. And depending on why you're doing a prescribed burn, the prescription might be different. In the same way that you go to a doctor, you might have a cold, you might have the flu, you might have COVID, whatever it is, the prescription you get is likely to be different. But still, we need a prescription. So with that in mind, let's go back to the overall picture. And knowing now that this is a very multifaceted problem, I'm very lucky that in my time here at NCAR, I've had the opportunity to connect across labs and see different aspects of the prescribed burn problem through the NCAR and UCAR lens. So the first aspect is fire effects, so the flame, and the mesoscale or microscale mesoscale meteorology lab, the research application lab, and the computational information systems lab all work on fire effects. On the air quality, so with the smoke parts, the atmospheric chemistry observations and modeling lab, again, Ral and our folks at UCAR COMET also have been working on air quality, including for prescribed burns. Then on the weather side, which we're going to see is quite important in understanding the prescription, again, M-Cubed and Ral, I've met with people working on NWP and downscaling in that capacity. And then the core of my visit here was in CISL with the CREDIT team, or the Community Research Earth Digital Intelligence Twin team, on weather emulators and approximations to weather models that could feasibly be run on different hardware. I'll talk about more of that in a moment. There's also the ecology piece that I'm putting in the top right corner, mainly because you'll see this bright green patch of fresh growth surrounded by the practically dead old growth underneath the tree. And you can see just the heterogeneity in what we consider fuel moisture that impacts the fire propagation. So that's work in collaboration with CISL and RAL. But in the more fundamental ecology part, I'm lucky to have met people at NSF Neon, who's also in Boulder, who have collaborated with CGD here at NSF NCAR. And the part that I'm going to be focusing most of the presentation on is the in situ sensing and data assimilation. So you'll see one of our sensors here and another one over here. And overall, sensing and data assimilation is a big part of the research happening at NCAR, including at CISL, Earth Observation Lab, UCAR COMET. Now, all of this is in support of the people at the center, which is the fire management personnel. And I'm also lucky that at NSF NCAR, the convergence science team has really been helping across the organization and bringing people from multiple aspects of the problem together and with external stakeholders to really make research impactful. So I'm really, really glad to have guidance from the convergence science team as well. Okay, so with that, let's focus on the fire management personnel. And in working with the land managers, fire ecologists, and other people within the space, you're going to get a prescription. And now, at the day of the prescription, you have to figure out, how am I going to meet this prescription? And broadly speaking, let's consider one axis here, which is a cold and humid to hot and dry. And I'm going to make a little bit of a popcorn analogy. So on one end, in the cold and humid side, we basically have an ineffective or a long burn, meaning that you wanted to pop your popcorn, you didn't actually pop your popcorn, right? So you didn't achieve the goals that you wanted because the environmental conditions didn't actually let you propagate the flame very effectively. On the other end, you have a hot and dry situation, which is like burnt popcorn. So you overdid it, and now you can't really enjoy your popcorn. And in a situation like that, it's a riskier burn, so usually you need a lot larger crew in order to make sure that the burn is well managed. But in between, there's this point where you can get nice, fluffy, really tasty popcorn, and that's what we want. And that's a case of both an effective and an efficient burn. So effective because we met the goals of the prescribed burns, one of the boxes I mentioned earlier, or a combination thereof. But it's also an efficient burn, which means that you're able to start the burn and your fire personnel are hopefully able to finish the burn before 5 p.m., wrap things up, go home, eat dinner with their family. Oftentimes, we really don't take the firefighters' time well enough in a research contest, I would argue. And there are definitely cases where we could be better allocating our resources or better managing the time that we ask firefighters to spend by understanding the conditions that we're doing the burning in. Okay, so with that in mind, let's break down the cold and humid, hot and dry into the separate axes, so relative humidity and temperature. And usually what you're going to see in a prescription is that they're going to give you bounds. So they're going to say the relative humidity should be between this bound and this bound, and the temperature should be between this bound and that bound. And then the intersection of these two bounds is the prescription envelope. So if we go back to the popcorn analogy, we can just put it on the chart here. So on the top left, we're cold and humid, and on the bottom right, we're hot and dry. And within the prescription envelope, we're going to get our nice, tasty popcorn. Now, even then, usually fire personnel will put a spot in the prescription envelope, which is the ideal conditions or the desired point. And the way to look at this is the prescription envelope, we're putting bounds, but largely speaking, as you go more towards the top left, you're going to get some kernels that didn't pop. And if you go more towards the bottom right, you're going to get some kernels that got burnt. And the closer you are to these initial conditions, the more likely you are to have nice, fluffy, tasty popcorn. Now here I'm just showing temperature and relative humidity, but in the prescription, there are other variables that people often think about. So this can relate to the wind, which can impact both the fire effects as well as how the smoke is going to go downwind, as well as the moisture content. So that basically determines, are you able to burn what you want to burn and not burn what you don't want to burn? So today we're going to really focus on the humidity and temperature pieces. So if we're looking at temperature and relative humidity, that also means that we're focused on meteorology. And the premier meteorology solution for this type of forecast is a National Weather Service spot forecast. But it also means that if every prescribed burn is pulling from this forecast, then they are very reliant on this forecast. And we'll see in a moment, the intentions of the spot forecast meet the operation day, but maybe not all conditions that the fire personnel might be interested in. So fortunately, the spot weather forecasts are available online, complimentary of our taxpayer dollars. So you can go to NWS forecast, you can click any of them, you can see the spot forecast. And in this case, I want to highlight one forecast that I pulled from the start of my graduate visitorship, which was right at the end of March. And I want to draw your attention first to the top left here. So the forecast is returned at 9:25 a.m. and the presumed ignition time for this prescribed burn is 10 a.m. So that's a 35-minute lead time. And this sort of day of lead time is pretty common. Why? Because for the spot forecast, you want something that's very timely. You want the most updated information as close to when you're starting to do the ignition as possible. Now, in this spot forecast, you will see certain criteria that are relevant to the envelope. So the main ones here, temperature, relative humidity, as well as some of the wind information and smoke information. And I do want to thank, in this case, forecaster Peterson from the Pueblo, Colorado NWS office for providing such a nice forecast. So what does someone like, in this case, forecaster Peterson, work with when they're making a spot forecast? This is a large a variety of data. Part of what they're going to look at is the fire weather outlook, which is going to tell them something about the conditions on the ground based off of the recent meteorological conditions, possibly over the course of like months. The next thing that they're going to look at is a numerical weather prediction. So in this case, throughout the rest of the presentation, we're really going to be focused on HRRR, or the high resolution rapid refresh model. They might also be looking at HRRR smoke to understand how it relates to the smoke dispersal that's going to happen from what the prescribed burn officials produce during the prescribed year. Now, when folks submit a spot forecast request, they're also supposed to put some in situ data. Technically, one data point is like the minimum, and that's supposed to include temperature, relative humidity, and eye level wind speed. In addition, the person on the ground is supposed to provide some information about what exactly on the ground is happening. So that's elevation aspects, so the orientation of the slope, topography, what they're planning to burn, and over what area. And the forecaster now has to put all these pieces together in order to give the fire personnel their best understanding of what they should face over the course of the day meteorologically. Okay, so, and again, one data point might be what the forecaster gets. So that's that third column, and that's gonna kind of continue through the presentation. Okay, so that is the spot forecast. But if in the field we don't have an internet connection, how usually does the spot forecast get to the folks? Oftentimes, there's some sort of base facility, so say like a fire station, that we presume to have a good internet connection. And what's going to happen is they're going to request and receive the spot forecast. They're then going to print out the spot forecast. They're going to bring the printout into the field. So this is great. No tech required, no internet required, very reliable. One of the issues here is, and this is actually on the spot forecast I forgot to highlight, but it says if the conditions change, please let us know. But it does mean that if conditions change, the prescribed fire personnel have to go back to the base facility, request the new one, wait for it, come back, and so forth, right? Which may or may not be what we want to do, right? So I'm going to highlight kind of two possible things that we might think about in a future scenario for fire management. So the first one here is, what if we had an on-site weather emulator? So this is, strictly speaking, in addition to the National Weather Service spot forecast, and potentially in collaboration with the NWS spot forecast team. So instead of sending and requesting a spot forecast, you're going to send and request weather data, broadly defined. And then what we're going to do is we're going to simply upload or download, really, that weather data to our laptop. And the argument is, okay, well, if we can get a weather emulator that can run on a laptop, so like, a laptop like this laptop, and we can bring that laptop into the field, then it allows the team to be much more dynamic, because you get into situations where the fire personnel are looking at the smoke and they can say, okay, well, that kind of matches what's on the spot forecast, but maybe there's something off that if I could just tweak something, things would line up, right? So what if we could bring a weather emulator into the field with us? Now, this type of development is part of the CREDIT Gen 2. So that's a large part of what I did during my graduate visitor program. And specifically, Gen 2 is able to process data beyond global data, which is really advantageous in this case, where we want to use a model like HRRR, or even more specifically, a limited area within HRRR. So now, CREDIT Gen 2 is not fully released yet, but coming soon, and look forward to another CISL seminar with CREDIT Gen 2 highlight. Okay. The second possible future that I want to bring up is, and yeah, hopefully AGU 2026. Look forward to seeing you all there. Okay, second future I want to highlight is, what if we could bring sensor networks to the field with us? And I would argue that we're very much making this future possible in the sense that we do have sensors at several prescribed burns, and we are planning to continue doing this. So again, in addition to the spot forecast, let's start from the other direction. So if you're in the field and you're a prescribed fire official, right? You might want to know the temperature and relative humidity that you're currently operating in. Now, there are cases where you have a sensor in the field, but that sensor is talking over cellular, over Starlink, whatever. It's getting the data out of the prescribed burn, but you can be right next to the sensor and not be able to see what the data is, especially across the whole network. So one of the things that we focused on with this sensor network is that they're bringing their own mesh network with the sensors, which I'll talk about in a moment, which allows the prescribed fire officials to collect and view the data in real time, in situ, no internet connection required. In addition to day of operations, it also changes how we might do the planning, because now we can see the actual data that we see in the field before we do that prescribed fire and change our plans accordingly. So allow us to potentially change what burn resources we say that we need. It also ideally helps the NWS Spot Forecaster, because we can provide that data with our spot forecast request in order to aid the forecaster in understanding what's happening locally on the ground versus what they see in the models. Which nicely leads us to what we're trying to achieve in this work. And again, HU 2026. Okay, so in this work, we're trying to combine two things. So the first thing is our weather model forecast, so that's the blue dashed line. And the second thing is the sensor data. So strictly speaking, the sensor data will tell you what's happening now and in the recent times, but it doesn't give you a forecast. The weather model will give you a forecast, and that can be from numerical weather prediction, can be from an emulator, can be from a downscaling model, it can be from insert your favorite forecast option, but it doesn't necessarily directly bridge the gap to what you see in a very hyperlocal sense. So the goal here is that if we can understand the bias between the forecast and the observation at a very hyperlocal level, ideally we can make a sensor forecast or a sensor network forecast that lets us understand what we expect to see in the future that adequately compensates for the difference between what the model says versus what you tend to see on the ground. And the important part here is that we need to do this from limited pre-burn data, because you generally speaking don't have a sensor already in place until we go and put the sensors. So there's two contributions here. The first part is the affordable sensor networks for prescribed burn. And the second part is the sensor forecasting with limited data. And I do want to highlight that we are going to be leveraging some insights from a very broad literature on sensor forecasting, mainly used in aviation. So if you have an airport, in this case, SFO airport, in order to generate the forecast for the airport, which is called the TAF, they are going to be doing this compensation usually. Now, for an airport, your airport is continuously operating in one specific location over an extended period of time. So when they do this calibration, they're actually using usually multiple years worth of data before they start the bias correction. Whereas we unfortunately do not have the luxury of doing that in this context. Okay, so starting with the first contribution on the sensor networks. So this project is a direct collaboration of Stanford Radio Club and Stanford Climate and Energy Policy Program. And I do want to highlight that this is very much a student-driven collaboration. So there are students that come to the Radio Club. They're interested usually in learning about Internet of Things or IoT. And the Radio Club, especially with our mentor, Dr. P. Mahowald, provides the technical expertise to understand IoT in the real world. And that real world part, in this case, is focused on developing tools for prescribed burns, which is really the expertise with the Stanford Climate and Energy Policy Program, which in this case, this part of the project is led by Dr. Jessica Yu. And fortunately, this collaboration has been going on for almost 2 years and is now part of my PhD dissertation. And yeah, there's been many students that have contributed to this across the years, sometimes for a quarter, sometimes for a lot longer. So when we're thinking about SMesh, we're thinking about 6 key design factors that specifically focus on the prescribed fire context. So the first part is that our sensors need to be portable, temporary, and rugged, meaning that we can show up right to the prescribed burn, put it right where we need to around the perimeter of the burn. And then after the smoldering period, we can take the sensors away and the preserve or the land is sort of back to normal. They also need to be rugged because we're often doing these prescribed burns in coastal mountain valley systems, oftentimes without additional infrastructure. So there's no concrete pad that you can put your sensor on and everything is nice and stable, for example. We also, because we need to ensure that we're collecting data, especially during the burn, but really before, during, and after the burn, we've opted for a very power independent strategy. So it's powered, in this case, by a car battery. And it also means that we're doing this generally without needing a network. So it's going to make its own distributed network. And in this case, the distributed part also means that if one sensor goes down, the messages can still be relayed across the network. So you don't have the single point failure that you might have in a direct, A to B, B to C sort of network architecture. Okay. So with that in mind, if we connect this to the prescribed burn context in a more spatial and temporal scale, which is going to run through the next few slides, a prescribed burn in California usually operates in the 50 to 100 acre range. Now, you usually get smaller burns as you get closer to homes, and you get larger burns as you get more into the wildland. For a 100 acre burn, we usually would target something around 10 sensors. And in this case, we're really focused on both the tactics, which is like a minute by minute, what is the prescribed fire official wanting to look at in terms of temperature and relative humidity, but more generally, kind of across the day, what's the strategy for the burn? Are we going to start on one end of the burn? Are we going to start on the other end of the burn? Are we going to start under trees? Are we going to start in the grassland? That sort of strategic decision. Now, for a 100 acre burn, if it was a square, that would look like roughly a 0.6 kilometer site length. And if we compare that to the weather models, in this case, like HRRR, which are operating at 3 kilometers, this is roughly to scale. So this outer box, if this was 3 kilometers, this would be the size of the prescribed burn area. So we're definitely within a grid cell, which is different than most data assimilation contexts where you have sensors across many different grid cells. Let's connect this to meteorologically what has to physically happen. So if we think about different scales, we often think about the spatial scale as well as the temporal scale. And a lot of our models are focused on, say, mesoscale or above. But the prescribed fire context has a mix of a time scale that's looking like a mesoscale time scale, as well as a micro scale that has to do with the tactics. So that's a much smaller scale. And if we plot this out, the key underlying hypothesis that we're working with here is that if the forecast from the model is able to cover the mesoscale and above, and the sensors are able to provide the microscale understanding, can we adequately combine the mesoscale information from the model with the microscale information from the sensors? And if we can do that, then we can actually meet the needs of the prescribed burn operations. So let's look at this with a real prescribed burn. In this case, this is the same burn that I started with at Pepperwood Preserve in October 2025. And on the left here, this is the HRRR grid overlaid on this area. And what I want to highlight is these are our sensors in orange, and this is the nearest HRRR grid. So it's definitely within a grid cell, right? And within this grid cell, there's many mountain and valley systems, right? Very different vegetation structure from grassland to shrubland to forest. You have more urban areas, more riparian river areas, which is wonderful. HRRR is not intended to capture all that, and we shouldn't expect it to, right? It's a mesoscale model. It does really good at the mesoscale level. Now we need to bridge that microscale gap. And if we look on the right here, we were very fortunate that we got an overpass from Planet satellites as well as Sentinel. And the Planet satellite information gives us the color information. So in this case, you can see the trees and the grassland, but you can also see the smoke from the burn. And Sentinel gives us an indication of the active burning. So these areas that are bright, and in this case, I've sort of loosely put the fire front in red, you can see where the active fires are. And because we have Sentinel and Planet, you can actually see, in this case, where they're starting a new burn down here, and you can see the plume developing. Now, in this case, for this prescribed burn, the folks at Pepperwood, they're super awesome. Preserve, highly recommend working with Pepperwood Preserve. They had many objectives for this burn, and they were willing to work in a more cold and humid case, working with the different types of vegetation that they might have. So they have grassland, shrub, and forest just in this burn area. Now, because they were operating in a more cold and humid kind of part of the prescription envelope, it does mean that the burn tactic here is a mosaic burn. So you can sort of see like the shards of a mosaic where the fire has to be reignited multiple times. Okay. So with that in mind, let's go back to the prescription envelope. And in this case, remember temperature, relative humidity. The prescription envelope in the next slide is going to be shown with a gray background. And in the rest of the presentation, I'm going to use this color bar to mean time of day. So specifically, what I want you to focus on is the darker colors are at night, lighter colors are at noon. That way you can look at the things that is moving as the environmental conditions change over the course of the day without having to keep going back to the color bar, okay? So let's plot the temperature and relative humidity. And the circle is the sensor, and the square is HRRR. So what I want to highlight is, one, they're not usually in agreement, which is fine. There's mesoscale phenomena that HRRR is not capturing. So in this case, again, the prescription envelope for Pepperwood Preserve was quite large in relative humidity because they were willing to effectively accept some unpopped popcorn, some kernels, because that was, in alignment with the goals of this prescribed burn. But the desired point here is quite a bit lower in relative humidity than the upper bound of the prescription envelope and kind of in the middle of the temperature envelope. So you can see, okay, this is nighttime, things get colder and more humid, and then the daytime comes up and we get hotter and drier. So we can follow how the environmental conditions are changing over the course of the day. And in this case, you might choose a strategy that burns different parts of the area depending on how close you think you are to this star, the desired point. Now, relative humidity is really advantageous when you're in the field. Unfortunately, as you can see, it basically forms like a line because relative humidity is very much dependent on temperature. So a nicer way to look at this from a mathematical perspective might be using specific humidity. And in this case, the distribution is more circular, which is to say not a line, it looks more like a circular blob. And in this case, we can make some argument that we can do one variable at a time, which is a little bit more difficult to make with relative humidity, though we will show results with both of these. Okay, so how are we exactly going to make the sensor forecast? So let's choose a variable like temperature, relative humidity, specific humidity. And we're just going to assume a linear model. So we're going to say the sensor network is going to be a bias and a slope away from the forecast. Now you might say, well, Daniel, you're in the machine learning group and you're just using a line. And yeah, when you plot the data, it looks like a line. I don't know what to tell you. I think a line sounds great to me if the data looks like a line. So we're not going to overcomplicate it. Linear relationship. Now, with this linear model, the natural thing to do is ordinary least squares. So we're going to do ordinary least squares. And specifically, the parameters that we're trying to regress is the bias and the slope. Now, I keep this figure on the right here because we can actually interpret what's happening in the ordinary least squares based off of the figure on the right. So this, the calibrated part, we're going to say is the mesoscale response. So the mesoscale model says X, and then X forecast, and then the response of that is X network. Now, it also means that everything that's at the microscale is going to be absorbed into the error term. And it's basically going to be omitted. Now, fundamentally, if we're willing to make some assumptions that your omitted variables are not completely correlated with your forecast, which we assume to be the case, especially based off of the figure on the right here, then we can loosely interpret the R squared as meaning how much of what we're seeing is explained by the mesoscale model versus how much is still remain to be unexplained because it's a microscale phenomenon. Okay, and I do want to make the disclaimer that these are student sensors. We are getting them direct from manufacturer. We're putting them in a suite. The sensors could also be biased. So I don't want to make the claim that our sensors are perfect, but we are going to use the sensor data as the direct target. So something to keep in mind. Okay, so we have the model, we have ordinary least squares. However, because we have a network, we can take another step, right? The network is going to have variability over time. So we can look at the mean across the network, and we can also look at the standard deviation. So what this fundamentally kind of implies is if you have a large standard deviation across the network, you are basically saying that there's heterogeneity across the burn area. If there's heterogeneity across the burn area, that sort of implies that you have microscale phenomena that you shouldn't expect her to capture. But if all of your sensors are in agreement with a certain variable, that gives you some indication that it's more homogeneous across the area. And then the mesoscale model, in this case, HRRR or an emulator, should be able to capture that information. So naturally, we can do weighted least squares in this case. Now, both ordinary least squares and weighted least squares, if we take the data before the burn, during the burn, and after the burn, really is a retrospective analysis. So it's good to understand maybe what we could have done or whatnot, but it doesn't actually help you if you're in the field and a prescribed burn official. What we need is a causal model that's only using the data up to now to predict the future forecast. So for that, we're going to use a Kalman filter. So we're going to have a joint state between the bias and the slope. We're going to put that together. We're going to estimate that over time. So there's going to be two parts here to the sensor forecast. One, we're going to look first at the retrospective analysis, as if you include all the data across all the days. So before, during, and after, what would you get? And the second is the forward filtering. So only using the data up to that time point to make the prediction. Okay, so let's look at the temperature again across the whole time series. So before the burn, during the burn, and after the burn. And what we see here is that HRRR and the sensor data is offset. And it looks like a pretty constant bias, right? It just looks like you shifted the line down or up, depending on how you want to look at it. Okay, so this is great. We can just plot this, and indeed, like I mentioned, it's basically a line. And ordinary least squares and weighted least squares in this case are directly in agreement. Okay, so that's really advantageous. You might say, okay, well, Daniel, well, yeah, the elevation is different. You can just compensate for the elevation. If you were to compensate for the elevation, you would expect something closer to like a 1 degree Celsius bias. In this case, we get closer to a 4 degree Celsius bias. So there is definitely some value in having your sensors in place to get the actual bias rather than inferring it directly from elevation. Though you could improve from just the model itself by accounting for elevation. When we get to humidity, it's a little bit more tricky. The mathematical issue here is that relative humidity is bounded 0 to 100%, which is a little bit dubious if you're doing direct linear regression. And it's also directly related to temperature. So if your temperature is wrong, you also expect your relative humidity to be wrong. But you could calibrate just the relative humidity. You will get an answer, and it does improve. Okay, so that's great. You can also use specific humidity, and you can see now that in using specific humidity, we've dealt with some of the temperature issue, right? The red line, which is the HRRR model, and the sensor data do track quite well. But interestingly, we do see more oscillation in HRRR than we see in the sensor data. And effectively, what that means for our regression is that we have a slope that is not 1, and we need to basically compensate for her moving more than what we see on the ground. Okay, so now we're going to move to the forward filtering, the Kalman filter part of this. And in this case, I'm showing up to this point in time, which is the dotted line. This is the forecast that we would expect. So early on, the common filter and ordinary least squares or weighted least squares do not quite line up. So in some cases, the common filter is actually closer to the sensor mean than ordinary least squares and weighted least squares. So the correction from the red line to the blue line is advantageous. In other cases, we see it overcompensating. And then once we get further in, then we actually see them track quite well. Now, I will say that I'm plotting here 1 sigma standard deviation with a common filter. Whether your standard deviation is adequate or not depends on your tuning and understanding of the noises involved here. So I will say there is more work to be done on the uncertainty quantification. So do take this blue shaded region with some few grains of salt, but it is something we're actively exploring. So we can look at it in a time series, but our common filter is operating in bias and slope. So it also behooves us to look at it in the space that we're actually running the filter in. So if we plot the bias and the slope, we might start with a prior that our system is perfectly calibrated. So that means that we have no bias and our slope is 1. So the forecast, whatever the forecast says, is what we expect to see on the ground. And what we want to say is we need these measurements or pairs between the forecast and the network in order to convince us that we actually need to apply a correction, right? So we're going to start with the prior here, that slope of 1, bias of 0 with some fairly large standard deviation. We're then going to get a measurement and have some understanding of the uncertainty in that measurement. And effectively what this measurement is saying, or this pair between the sensor and her, or sensor and your emulator, is saying is that the system should be on this line somewhere. We have some uncertainty of that line. Now what that means is that our estimate, which is the mean and the standard deviation, should be drawn towards this line, but you don't know where along this line you're going to get. So we're going to do one update here to get a posterior. Now to really get down the bias and the slope, you need to wait for the whole meteorological system to move, because you need different pairs of sensor and her in order to get the line to move in orientation. And that's going to better let us figure out where we are in this space. Okay, so in order for the uncertainty to be adequate, we need to account for uncertainty from multiple parts. So the parameter uncertainty, which the common filter is handling by maintaining the state, as well as the forecast uncertainty, which deals with how the forecast is expected, our certainty of the forecast is intended to change as we look further into the future, as well as what do we expect in general in terms of accuracy of the forecast, as well as the sensor network uncertainty, which nicely we can get because we have multiple sensors. Okay, so when we look at this in terms of temperature, and I'll wait for the animation to start again, you'll see it start from this overall area. And at first, it overcompensates again on this line because we don't know where we are on this line until we get enough measurements and it lines up with orange and green, which throughout this presentation is the ordinary least squares and weighted least squares. And if we look at the final analysis at the last day, then we do roughly get back what ordinary least squares and weighted least squares said as implied, because our point and ellipse sort of line up there. So what this sort of means practically for a fire personnel official is that you want about 3 days of sensor data before the burn in order to adequately do this calibration. If you don't have 3 days, you might overcompensate in one direction or another, and it might not generalize as well as you would like. Okay, we can also look at relative humidity. So this is same thing as before. Again, uncertainty quantification still in the works. In this case, generally, our sensor data we see is drier than what her predicts in the model. So we can again look at it in the space that we're running the common filter. And in this case, we can see it sort of narrowed down, but it sort of gets stuck. And we think this is partly because of the temperature dependence, and we're just going directly through relative humidity. And if we look at the final result, we do end up close to ordinary least squares and weighted least squares, but it takes about 5 days to calibrate the humidity, the relative humidity. In contrast, we can look at specific humidity, which, as we noted before, because it's a little bit more separated from temperature, HRRR is already tracking quite well with the sensor data, but we can kind of improve still over that. And we can, track with the adequate uncertainty, again, if you believe the uncertainty quantification thus far, into what we see on the ground. So again, if we look at it in this space, the specific humidity parameters are a lot tighter in this case. And we are able to, again, get back to the ordinary least squares and weighted least squares retrospective fit with about 3 days worth of data. Okay, so I mentioned kind of this prescription envelope. So I'm going to wait for the animation to start again. But we're going to have circle as circle as sensor, square as HRRR, and triangle as filter. Again, desired point is here. And what I want to kind of illustrate is there's still not fully matching between what the sensor says versus what the filter says. But generally speaking, the triangle is closer to the circle than the square is to the circle. And that's the goal here. Now, again, we don't expect triangle to be directly, overlapping with circle because microscale phenomena that we wouldn't expect to capture. But we are able to see an improvement. And in the publication, hopefully at HU, we'll have some more quantitative metrics that are currently in the works there. And again, we can look at this in specific humidity. Very, very similar story. Okay, so I mentioned the uncertainty quantification. For those that have used HRRR, you've probably been screaming, "Oh my gosh, Daniel, you can use a time-lagged ensemble." So yes, we are looking into this. How exactly to best use the time-lagged ensemble within the measurement noise and account for the correlation is something that we're currently exploring. There is some things to be aware of in terms of mathematically. Otherwise, the uncertainty at, say, the 48-hour point ends up being much smaller than I'm willing to believe. So this is current work, but what we're kind of showing here is the lighter colors is farther into the future, and the red colors is closer to the analysis point of the dashed line. And you can see cases where, for example, the temperature drops down or increases as you get closer to the valid time here, which surely makes sense, right? Because you get more information, the weather system may have moved one way or another. The newer data may move from the 48-hour forecast. We can again do the same thing with relative humidity and specific humidity. I'll show both, but the main point here is that the humidity variable time lag ensembles tend to have much larger standard deviation than what we expect, or than what we see in temperature. So this is something that when we're looking at the emulator, so this could be HRRCast, it could be from CREDIT or whatnot. When we're generating ensembles, we do sort of need a well-calibrated uncertainty in order for this to hold in the forecast system. Okay, and then lastly here with specific humidity. So I think I'll cut it there. Okay, so if we go back to the fire official, again, at the center of what we're looking at here, the main takeaway is 3 to 5 day sensor lead time. You can do more. So you can set this, if you think there's a window where you might do a burn, just budgeting at least 3 days before the burn, we should be able to provide some calibration over what we see into the future. And again, the whole point here is that on this cold and humid to hot and dry, popcorn analogy, we do want to help the prescribed burn team or support the prescribed burn team in getting to that effective and efficient burn. So kind of summarizing here, we looked at affordable sensor networks for prescribed burn in collaboration with the SMesh team, as well as doing that sensor forecasting with limited data. And we have a lot of things coming to soon, especially with CREDIT Gen 2. So please keep your eyes open for that next CISL seminar. Okay, I do want to provide some thank yous here. So first, the SMesh team for really making the sensor and collaboration possible. So Dr. Piet Mahowald for all the technical advising, Dr. Jessica Yu for the connection with SEP and leading the project, the many, many students involved, Tomcat for funding my PhD and letting me explore such an interdisciplinary topic that would usually not be possible in a lot of funding options. NCAR CISL team and the EdEc team for supporting me in this GBP, as well as all of our sponsors and my main lab at Stanford, the NAB lab, and Pepperwood for letting us attend this burn and collect all this data. Kind of highlighting the teams across NCAR that I'm so lucky to have been able to talk to and have offered such great advice throughout the visit. It's really across the whole organization, and I really forgot to take so many pictures. So if I met with you and I forgot to take a picture, I'm really sorry. But I am very thankful for your guidance. And yeah, thank you to all of the interns throughout here, especially Mika Lau, who was my fellow intern the first month here, where it was nice and quiet in April. But let me just make sure I'm not forgetting anyone. Okay, yeah. Pepperwood team, especially Devin, Ryan, Laura, the EdEc team, Jerry, Megan, Dana, as well as the SciParks team, Virginia and Jessica, for letting me, join the SciParks interns. Thank you also, yeah, especially to the credit team, DJ, John, Charlie, Caitlin, Kevin, and kind of the whole CISL impact group with John Klein, the DART team, Mohang, Kevin, CISL director Doug for such fun insights at the start of my GVP. And definitely also want to thank the shuttle driver team, I should say, that really got me to NCAR. I have to walk up the hill every day. So real big thank yous there. And I'm happy to take your questions.
All right, who wants to go first?
For those of you online, if you want to ask a question, feel free to either raise your hand or drop it in the chat. Otherwise, we can get started with questions in the room.
Yeah, so you mentioned like the growing uncertainty from her. Is the right way to think about this as like the network's extending the envelope on which her is, or whatever, if it's an emulator, whatever forecast, it's extending the envelope to which it's accurate?
Potentially. I'd say that to what extent it extends the envelope depends on what level of uncertainty you're willing to deal with, right? So let's say, for example, the okay, let me go to one of the popcorn slides. Yeah, we'll use this one. Okay, so say for example, per 48 hour is saying that you're somewhere in the middle here, right? If you have a 5 degrees Celsius uncertainty at the uncertainty level you're willing to deal with, you're totally fine, right? So if you're 25 degrees Celsius in this case, you're still within 20 and 30, good to go, right? So you know you're going to be in prescription. If her is saying, actually, you know, 2 days out into the future, you're going to be at 31 degrees Celsius, and the uncertainty is 5 degrees Celsius. Now we have to make some decisions, right?
That's like almost out of bounds. Yeah,
exactly. So now what you can calculate is, if your uncertainty is well calibrated, you can say, what is the probability that I end up outside of the envelope, right? And that's kind of what we would want to calculate. So your interpretation of what uncertainties are acceptable will depend, one, what is your prescription envelope? And two, where are you in that prescription envelope with respect to the goals that you're trying to achieve?
cool. Also, the relative humidity one, it just feels so Clausius Clapeyron. I feel like you're better off in specific humidity.
Yeah.
It looks like Clausius Clapeyron.
Exactly.
Yeah.
All right, other questions? Even online?
I was like,
Yes. So you said that the sensor should be set up at least 3 days before the prescribed burn for calibration, right?
Yeah.
What made you land on 3 days as a like good amount of calibration time?
Yeah, so the 3 days is based off of the retrospective analysis. So the context here is, if you can get your bias and slope to values and uncertainties that are similar to weighted least squares and ordinary least squares, then we're going to say that we're good at that point. Now, I will say that you can tune the common filter to go more towards ordinary least squares or more towards weighted least squares. So yeah, the aim is, are you in that ballpark with ordinary least squares and weighted least squares? Exactly which one you choose or do not choose, and the noise parameters that you choose for a common filter. These are all going to be part of that uncertainty quantification work that is still ongoing. Next question from Shima, I think.
Great job, Daniel. I have a question about the plot that you were showing. Is this all from one case study, or you can move the stations and still like add to your data set for this analysis?
Yeah, definitely. Thank you for your question. Yes, so here the running example in this presentation is the Pepperwood October 2025 burn. I do have, or the SMesh team has data from other burns as well. The idea here is to do the parameter optimization on this one burn and then apply it to the other burns. The reason here is to avoid overfitting to every single burn. But yeah, that's ongoing work. I can, different burns, if it's in a redwood forest or if it's in a grassland, whatever, we have seen differences in that sort of sense. But in terms of the final analysis in this work, what I'm showing here is for that one burn. But you can apply the technique to whichever burn you would like to look at.
Sounds great. But do you expect to see like large differences, especially for the different topography that they could potentially face, adding to the meteorology and everything else that might be quite different? And you mentioned the land surface interaction.
Yeah, exactly. So some of our burns happen in environments that are very heterogeneous, have very sloped terrain. And in those cases, in the data itself, we've already seen more variability between the sensors. It does depend on some meteorological conditions that we're not including here, like your cloud cover, where is your fog and stuff like that. Like earlier in the morning, especially. But largely speaking, that is part of the ongoing work here. Cool. Other questions? Yeah.
What motivated your decision to put sensors around the perimeter of the area that you're doing the prescribed burn, rather than maybe a more like uniform distribution throughout the entire area in the center? Did you find it to be more well calibrated to put on the perimeter?
Yeah, great question. Okay, so it's a very practical answer. So the practical answer here is getting permission to put something outside the burn much easier than inside of the burn area, number one. And number two, although our sensors theoretically can handle it, exposing it to the flames is not something that we've like directly sort of tested in a very concrete sense, and we do want to be careful about not putting burnt plastic into the ground and stuff like that. So we are working on, or we do have a version that's smaller that could be put more mobily inside the burn area. This data here does not include that sensor form factor, but it is something that we've looked at. Now, in terms of to what extent we think it would change or not change, depends a little bit on the pre-burn, during burn, or after burn. So during the burn, we're definitely going to get more exposure to the heat of the flame if we're inside the burn perimeter than outside the burn perimeter, right? And we would have to be careful about not including that in the retrospective analysis, because that's definitely like a very micro scale part that's going to skew the retrospective. There are ways to do this with a fading memory common filter and other varieties like that, which we have looked at. For this sort of case where they're outside the burn, the fading memory didn't really change that much. The other part that I didn't really touch on in this presentation, but our sensors do measure smoke, so PM 1, 2.5, and 10. And if you're inside the burn area, you're probably getting a better estimate of the upper bound on the smoke generation than you would get at the perimeter. So that's one of the parts that's motivating us to consider getting, more into the area.
But one last question from online.
Yeah.
From Seth Shalit. Great presentation. Related to the 3-day calibration time, one issue that can be a challenge is site permitting and site access. Certain permits may give you only a day of site access. Do you anticipate in the future being able to speed up the 3-day advanced calibration window?
Yeah, thank you so much for the question. It depends on sort of, what level you want, right? So like, even if you set up the sensors an hour before you submit your HRRR forecast, technically you're getting an hour's worth of data that is different than your single data point that you would be giving to the spot forecaster. So you do already provide value in that case. Now, in our cases, for the burns that we've gone to, usually they've been much more willing to give us access before the burn with sufficient lead time than day of. Usually day of, like for some of the burns day of, they're like, oh, please just don't be around. We don't want you to interfere with anything. So for that context, that's how we've been sort of negotiating with the folks on the ground. In terms of how early we go, the sensors are intended to be able to last about 30 days under good conditions and whatever. So, we can provide quite a bit of lead time, and the idea is to sort of stay out of the operator's way for most cases. But there's definitely different concept of operations that we have considered throughout the project.
Right. With that, if you have more questions for Daniel, you'll be at the ice cream social at 10:45.
I will be at the ice cream social. And if there's questions online, you can also email me.